Now, so that was a major development with regard to the NMR spectroscopy. The Fourier transform NMR was a major revolution. Increase the sensitivity of your NMR spectrometer quite manifold, and therefore you could actually do experiments with your molecules at natural abundance of carbon 13. Now, the Fourier transform NMR had another important development, and that is that excitation of your spin system and the detection of the signal are separated in time. This is called as the segmentation of the time axis. You excite your spin system by applying an RF which rotates the magnetization here, and when you are actually collecting the data as an FID, you are not doing anything. Okay? Therefore, the excitation and the detection are separated in time. So, which means that you can do various other kinds of manipulations in between. Remember that the FID which I collect as a function of time after the pulse is removed, at every point in the FID I have full frequency information. The frequency information is not lost. Therefore, if I create a small gap between the excitation and my detection of the signal, suppose I create a small gap, I am in fact not going to lose anything with respect to the frequencies, but it gives me a window, a time window, where I can do various kinds of manipulations. And this was exploited very elegantly to develop what is called as two-dimensional NMR. What is done here? The segmentation of the time axis is indicated in the way that is shown there. You can see as 4 periods are indicated: preparation period, evolution period, the mixing period, and the detection period. Now, preparation period is basically your excitation of the pulse sequence, of excitation of your spins, and then you introduce a time gap which is called as T1, which is called as evolution time, and then you have a so called mixing which mixes the various spins, and you actually detect the signal as a function of time in the period T2. Now, I do this experiment several times, not just once. What do I do in this? I keep incrementing this T1 period. Systematically I keep incrementing. As you can see, from top to bottom there are multiple experiments done, right? In the first experiment the T1 period is 0. The second experiment, certain time period T1 is given, certain increment is given. The third experiment you have additional time increment which is 2 times of the whatever was given in the earlier, and the fourth experiment you again have an additional increment. So you systematically increment this T1 in a regular manner so that you can collect a large number of FIDs at the end. So for each one of those you have an FID collected. So there are several experiments done and you collect an FID for each one of those, and that is indicated at the bottom here. Then you can see various FIDs, one FID corresponding to value of T1 is equal to 0, then you have another one which is going for a different value of T1, and the third one for a systematically incremented T1 value. You increment, the increment is kept the same every time. Therefore, what I have done here, I have created a new time variable which manifests itself as a particular modulator of the detected signal in the end. So therefore, I generate a 2-dimensional data matrix which is also indicated here. I generate a 2-dimensional data matrix which is in principle it will give you a 2-dimensional spectrum. How it is possible? You can see that here, and if you go through this individual traces, then each one of them which is first Fourier transform, you get one NMR spectrum, and then you have the second NMR spectrum, third NMR spectrum, fourth NMR spectrum, things like that. Each FID is Fourier transformed to generate the individual spectra. Now, each spectra, now you look at it from the point of view of the intensities. All of them have different intensities. So one of them has a positive intensity, then you have a negative intensity, some you have a 0, then it again picks up positive, negative, and things like that. Therefore, if I were to go from bottom to the top or top to the bottom, which is all those traces at different time and different points along the spectral region there, these are plotted on the right side of the picture, and you can see that they are also going a time dependent modulation. So the points which are there is a function of t1 if you see below, then you go from the various time points A, B, C, D, E, F, G. These correspond to various points on the NMR spectrum there, and all of them at each of those, you take a vertical cross section, they have different kinds of behaviors with respect to the time, because what is varying there is the t1 time. Therefore it is a kind of a pseudo free induction decay, is a pseudo FID. Therefore if I do a Fourier transformation along that, then again get a frequency spectrum, again get a frequency, because there is a frequency information present there. And therefore if I now do a two-dimensional Fourier transformation, I will get a two-dimensional spectrum. So this is the principle of two-dimensional NMR. The foundation is laid in the Fourier transform NMR itself. So put that in different words, you have here the preparation, evolution, mixing and detection, and I have here a schematic of the two-dimensional spectrum. So let us look at it. Suppose I create a certain frequency during by the excitation, the frequency is evolving in the time period t1 with a particular frequency, and during the mixing I do something which is again a trick. So I do some operation there, which is by application of pulse or delays and things like that. So then when they actually detect the signal, I may be transferring some information from this particular spin to the next spin in the t2 period. The spins which were going on with the frequency, particular frequency in the time period t1, let us say if I call it as omega A, and when I go to the t2 period, I transfer part of the magnetization from omega A to omega B, and some of it will continue as omega A. Therefore if I look at the horizontal cross section there, I have the red signal which has the same frequency in the t1 as well as the t2 period, and that will produce me a signal at the diagonal in this two-dimensional plot. So if you look at the frequencies that are present there, then you have along the two frequency axis, you have a blue signal. Let us say you look at the blue signal, it has the same frequency along both the two axes of your spectrum, and that we call it as the diagonal peak. That means there was a frequency omega B which was present in the t1 period, it continues in the t2 period also as a omega B frequency. However, because of the mixing, there is a small transfer of this to omega A, and that results in the yellow cross peak at omega A. If you go horizontally over there, you go horizontally from here, blue to the yellow, this is the peak which is coming because of the transfer of magnetization from the blue spin to the red spin, or the omega B to omega A. Likewise in the top as well, you have a transfer of magnetization from omega A to omega B, which produces a yellow peak. The red one produces a yellow peak. So these off diagonal peaks are actually called as the cross peaks, and these are very important because these tell you what kind of interaction is present between these two spins, between these two blue and the red ones. Is there an interaction between them? You don't get these transfers from one spin to another spin just like that. There has to be a kind of interaction between them. Depending upon what sort of interaction is present, you will have the transfers possible. So a particular example, there are many different examples which are present here. Depending upon what sort of interactions are present, you use different kinds of mixing sequences, mixing operations, which will transfer magnetization from one set of spins to another set of spins, and that produces a cross peak. Therefore this will allow you to display your information about your molecule, about the structure of the molecule, which spins are coupled to what, in what way they are coupled. You display them in a plane rather than on your one-dimensional spectrum. So this was a major revolution, and you will see its implications very soon. So one particular experiment which became very important is the so-called 2D J-resolved spectroscopy. So here the pulse sequence, now you see, now the segmentation of the time axis is done in such a way that you have a first a 90-degree pulse, then you have the period t1 by 2, then 180 degree pulse, then you have again a T1 by 2 period, and you collect the data as a function of time in T2. In the earlier slide I had this T1 period evolving during, and that is systematically incremented. Now in this experiment what I have done is I have put a 180 degree pulse in the middle of the T1 period. So therefore 180 period splits the evolution period into two halves, but on both sides this systematic incrementation goes on. Now this period 90 tau, 180 tau, or the T1 by 2, 180 T1 by 2, that sequence is called as the spin echo. Now the spin echo, as I said, is a major discovery, and in this period it so happens that the chemical shifts are refocused. So whatever is the chemical shift present at the beginning after the 90 degree pulse, that the spins will be evolving, but that will be completely refocused at the end of the second T1 half period. Therefore it appears as though the chemical shifts did not matter to the experiment in this sequence. So that is called as the spin echo, but the coupling constants between them, that is still operational, that is still present, and that modulates what is happening in the T1 period. At the end of the second T1 half period you get an echo, saying that echo amplitude is modulated by the J coupling, and then when you collect the data as a function of time T2, you will have both the coupling and the chemical shift information present. So therefore along the one of the axis you have the chemical shift and the coupling information present, and on the other axis you only have the coupling information present. So what is the consequence of this? So if I were to record an NMR spectrum of this after a two-dimensional Fourier transformation, consider a simple molecule which has a doublet and a triplet, and then you notice along the F1 axis or the omega 1 axis I have only the coupling information. On the F2 axis I have both the coupling and the chemical shift information. Therefore I will generate a spectrum which is indicated in the bottom half here, one doublet, one triplet, which will come here, and there is no chemical shift along this axis, but there is chemical shift along this axis. So now what I do is I actually do a shearing transformation here, instead of the angle which is present there in this spectrum. You have an angle going like this, I do not want to have that angle. I move these peaks like this in such a way that I get the 3 peaks along the same vertical line and the 2 peaks along the same vertical line there. So then that means that if I were to look at this total spectrum, if I were to take a projection along the vertical axis, then I will have one peak for the doublet and one peak for the triplet. That means I have decoupled this spectrum from both the triplet and the doublets are now giving single lines. On the other side, of course, on the horizontal side you will have the two chemical shifts present. Therefore this is called as J delta separation. The chemical shifts and the coupling interactions are separated along the two frequency axes. On one axis you have only the coupling information, and the other axis you have only chemical shift information. So this is a significant simplification with regard to the display of the NMR spectrum and extraction of the parameters. We need to collect the chemical shift as well as the coupling constant information for understanding the molecular structures. So here is an experimental example. You can see here that you have various kinds of protons present. So on one side you have a doublet, then you have a triplet, then you have a doublet of a doublet, there are 4 lines, then you have a singlet over there, then you have once again a triplet, a singlet, and then you have doublet of a doublet, then again you have a doublet of a doublet. So many different kinds of fine structures you are able to see, and at different chemical shifts. So this is a valuable information with regard to the chemical structure of the molecule, and you can determine the molecular structures very well. In very complex systems you can do this because they will get separated out on the 2 frequency axis. Okay. Now the basic principles of this, they were actually published in very major papers by this Richard Ernst group. One was I already talked to you about the correlation spectroscopy. You have the cross peaks and the diagonal peaks, and that experiment is called as COSY, and that is the one of the very first experiment which was performed. And then you also have the NOESY. The NOESY is an experiment which tells you what sort of an interactions are present between the protons in your molecule. I told you the cross peaks which appear in your two-dimensional spectrum depending upon the nature of the interactions, and here are the two interactions separated. You have two different experiments to display different types of interactions. In the Cauchy spectrum, you have the interaction of J coupling, which manifests itself in the cross peaks. In the Nosy experiment, it is the dipole-dipole coupling which happens through space, and that manifests itself in the cross peaks. And this is structural information, right? See, if I have the distance between two protons and I know what kind of a structure it must have. If the molecular structure changes, the distance between the two protons changes, and this was actually a major development which happened, and that is actually led to the application into protein structure into larger molecules, protein structure determination, and so on. And in fact, as I told you, in fact that actually led to another Nobel Prize to Kurt Wittrich and in 2002. So this is the Cauchy experiment. I repeat the same what I showed you earlier. You have here the red and the blue, and you have the cross peaks. The cross peaks are in yellow. This is the correlation, generalized correlation spectrum. Now the yellow peaks will appear either because of the J coupling or because of the NOE coupling. NOE is a dipole-dipole coupling. The dipole-dipole coupling is dependent on the distance between the two protons. It goes as the inverse sixth power. The intensities of the peaks in the Nosy spectrum goes to the inverse sixth power. And Nosy stands for, by the way, nuclear Overhauser effect spectroscopy. Nuclear Overhauser effect depends on the inverse sixth power of the distance between the two protons. So therefore, you will have two different kinds of spectra depending upon how you actually perform your two-dimensional experiment. For the Cauchy experiment consists of a very simple experimental scheme. You have here a 90-degree pulse, then you have a T1 evolution period, then you have a second 90-degree pulse, and you have the T2 evolution detection period. So this is the simplest of the experiment, and you have two frequency axes generated by systematically varying T1, and then you do a two-dimensional Fourier transformation and you get a spectrum like this. Here is an example what sort of a spectrum you get for a simple dipeptide. On the left hand side you have the molecular structure of a dipeptide. You have the central amino acid is the valine group, valine amino acid. Then you have the polypeptide backbone going in this direction. So you have the N, C alpha, C dash N, and this is the N is of residue I, then C alpha residue I, and carbonyl of residue I. Then you have the amide of residue I plus 1. So you have the peptide group at the CO and H. Then on the C alpha you have the valine side chain, you have the C beta H and two CH3 groups. Now what are the couplings present here? Let us look at the couplings. The couplings are, you can have 2 bond couplings and 3 bond couplings or 1 bond couplings. So here we are talking about proton-proton couplings, and the proton-proton couplings are 3 bond couplings here. You have the coupling from the amide proton to the C alpha proton, which is the 3 bond coupling, and then you have from the alpha proton, this is the C alpha, from the alpha proton you have a coupling to the C beta proton, and then from the C beta proton you have a coupling to the 2 methyls, which are the 2 gamma protons. Okay, and so therefore, and there is no coupling between the amide proton of the next residue to any of the protons in the previous residue. Therefore, what do you get in your Cauchy spectrum? Cauchy spectrum displays what all couplings do you have in your molecule, and therefore you will see it consists of only those cross peaks of particular amino acid. So in the spectrum, if you see, which is indicated there also, you have the cross peak from the amide proton to the alpha proton. From the alpha proton you have to the beta proton, and then from the beta proton you have the cross peaks to the 2 gamma protons, and all of these are indicated by red symbols. There is no coupling between the 2 gamma protons, between the 2 methyl groups there is no coupling, and therefore there is no cross peak between the 2 gamma methyls. So therefore in your spectrum, if you get a pattern of peaks like this, NH to the alpha, alpha to the beta, beta to the gammas, then you know for sure this will actually represent the valine group in your molecule. Now here is an example of a spectrum which takes you in a little bit more detail. For a 2-spin system, if I have only 2 protons in my molecule, then I will have a doublet for each one of those. But in your 2-dimensional spectrum, where I indicated you have one peak for on the diagonal and one peak on the cross peak of diagonal peak, but in fact it turns out that this fine structure is reflected in the diagonal as well as the cross peak. So therefore, here each one of those, the diagonal will have 4 components, the cross peak will also have 4 components, because along both axes you have 2 doublets. So the doublet into a doublet, which will actually give you along both axes 2 doublets. If you take any cross section, there will be a doublet for each one of those. Even importantly, another feature to notice here, that if you took a cross section, horizontal cross section like this, through the top, for example, through a top portions which are indicated, then I have here positive negative signal. You have negative signal and a positive signal, both are absorptive line shapes going cleanly like this, and then you have here also 2 signals, but these line shapes are different from these line shapes, and these are called as dispersive line shapes. The dispersive line shape goes like this and like this, then like this and like this. So this is the dispersive line shape. So the diagonals have dispersive line shapes, whereas the cross peaks have absorptive line shapes. Also notice that there is a sign difference in the cross peaks. The cross peaks have absorptive, positive, negative, which represent as plus and minus, and the diagonal has dispersive but the same sign, which is plus plus. And if you took a contour diagram, because these are the coordinates and the intensities of the peaks are typically going up like this. Now if I make a contour representation of this spectrum, that is shown at the bottom here, and you can see in the cross peaks they are clearly indicated, very well resolved doublets, positive and negative, negative positive, and in the diagonal is quite a messy structure there. This is because of the line shapes. The dispersive line shapes don't produce very fine appearance of the cross peaks, and this actually results in loss of signal to noise and signal resolution in your spectrum. So therefore what you do is you developed a new experiment. We will not go into the details of this experiment, and this is called as a double quantum filtered COSY, and this consists of an experimental sequence which is indicated on the top there. Now you have a 90-degree pulse, the T1 period, a 90-degree pulse, then a short time gap, then you have second 90-degree pulse, and you collect the data as a function of time T2. And this results in what is called as a double quantum filtered COSY experiment. This has a better resolution. The comparison of the COSY and the double quantum filtered COSY is indicated here. You can see the diagonal peaks as well as the cross peaks, they are much better resolved. You have fine structure. An improvement over the COSY experiment was done by what is called as the double quantum filtered COSY. You can see here that this consists of a simple modification of the COSY pulse sequence. You have a 90-degree pulse in the beginning, and then followed by the T1, and then the second 90-degree pulse. This up till here it is the same as the COSY, but then you put a small gap, and then you put the third 90-degree pulse, and after that you collect the data as a function of time T2, and then you do a Fourier transformation, 2-dimensional Fourier transformation, which will give you a 2-dimensional spectrum. But in the bottom, the spectra which are shown indicate to you a significant improvement. You compare the COSY, which is on the left side, and the double quantum filtered COSY, which is on the right side, and then you can see both the diagonal and the cross peaks have a fine structure which is very, very clear. So on the diagonal also you have all the 4 components very well resolved, and the diagonal and the cross peaks also, they are very well resolved. An implication of this is shown in the bottom spectrum also. This is an application to a protein here. Now you see on the left hand side here you have the COSY spectrum of a particular region of a COSY spectrum of a protein here, and there all the diagonal peaks are so huge that you cannot see any cross peaks which are close to the diagonal, and they are all masked, and therefore you cannot do any analysis of your spectrum in this area. But in contrast, the one which is on the right side, which is the double quantum filtered COSY, shows clearly the diagonal peaks, a number of cross peaks which are close to the diagonal, which can be easily analyzed. Therefore, you can connect the various peaks in an unambiguous manner in this double quantum filtered COSY. This was a major development. Such developments have been happening, and one of the other development which has happened, which is called as the J-scale COSY experiment, which is once again a small modification from your experimental sequence. You have the 90-degree pulse, then you have the T1 period, then you have a spin echo kind of a sequence, tau 180 tau sequence before your 90-degree pulse. So therefore, in the COSY sequence what we had earlier, you introduced a in between a spin echo kind of a sequence, tau 180 tau, that is the spin echo kind of a sequence, and then followed by the 90-degree pulse. So you have T1 tau 180 tau, and then you have the 90, and followed by the T2. So the two 90-degree pulses are separated by the period alpha T1. The consequence of this is that the coupling constant which is present between two protons appears magnified along the omega 1 axis, along the after you what you get after the two-dimensional Fourier transformation along the T1 axis, you get the omega 1 axis, and there the coupling constant appears magnified. So what is the result of this? The result is that the plus and the minus components which are present in the cross peak, they actually get separated out much more. Therefore, there is no cancellation of the cross peaks here. So this was the major, this was the implication for the J-scale COSY. And you can do this further. Various kinds of modifications have been made, and the same spin echo sequence what you saw earlier is introduced in this experiment as well. This is called omega 1 decoupled COSY or constant time COSY, and you see here it is the same as the J-scale COSY pulse sequence, except that the two 90-degree pulses which are present there, they are separated by a constant time period called delta. It is no longer alpha T1, but it is a constant. So therefore, you have a delta time period which is constant between the two 90-degree pulses. In between you have the T1 period, and then in the spin echo sequence tau 180 tau sequence. Following that you have the T2 period. What is the consequence of this? The consequence is that along the omega 1 axis there is no coupling information. Coupling information is completely eliminated along the omega 1 dimension. Coupling information appears only along the omega 2 dimension. Therefore, your overlapping multiplets which are shown in the left side here, they get clearly resolved in the spectrum which is shown on the right side. The constant time COSY shows clearly the separation of the multiplets which are present here, which could not be discerned in the left side spectrum here. So likewise, a large number of developments have been happening, and that have revolutionized the applications of NMR in chemistry. To work with a large number of molecules, very complex molecules, it has become possible to do so. So here is another illustration of an experiment which is called as TOXY. This relays information from one spin to another spin in your molecule. Suppose I have here A, B, C, 3 protons, then in the COSY spectrum I see a cross peak from the A to the B and B to the C. But in the TOXY spectrum, whose sequence is shown on the top there, we will not go into the details of the sequence, but these are all now push button kind of experiments. On the spectrometer, you hit a key, you can do a TOXY experiment, you have to indicate the parameters. So then you will generate a spectrum of this type. So what is the information present here? So in the COSY spectrum, as I mentioned to you, if I have 3 protons A, B and C, if there is a coupling between A to B, I will have a cross peak. I will have a cross peak from B to C. Now in the TOXY spectrum, you will not only have A to B cross peak and B to C cross peak, you will also have A to C cross peak. Okay? Therefore, it increases the information content in your spectrum. So therefore, you can see in the spectra below down that the COSY spectrum has the fewer peaks compared to the spectrum on the right hand side, which is the TOXY spectrum. The TOXY spectrum shows you a whole lot of connections between the various protons in your molecule. So this will unambiguously establish what is the kind of a pattern of coupling between the various protons in your molecule. So these have become extremely important applications, important developments, and they have allowed analysis of complex spin systems in organic molecules and large number of molecules. The next important development which I want to tell you is what is called as the nosy, or it is also called as the XC in certain cases. Now this experiment consists of 3 90-degree pulses. As you see here, you have the first is the 90-degree pulse, then you have the T1 period, then you have a second 90-degree pulse, then you have a so-called mixing period, and then you have a third 90-degree pulse, and then the detection happens as a function of time T2. Now tau mix, which is the mixing time which is kept fixed, and T1 is the one which is systematically incremented to generate a 2-dimensional spectrum. Now this experiment displays the dipole-dipole correlations. Unlike the COSY which displayed J correlations in your molecule, this experiment displays the dipole-dipole correlations which happens through space, is a through space interaction, and therefore this has a completely different kind of information in your molecule. For a simple 2-spin system, it appears like this. You have two kinds of schematic representation of the spectrum. Here you have two different kinds of situations depending upon whether your molecule has slow rotation tumbling in your solution or fast rotation in your solution. So and that is represented by what is called as omega tau c. If omega tau c is much less than 1, it means the molecule is tumbling very rapidly in your solution. On the other hand, if omega tau c is larger than 1, then the molecule is sluggish, it is a larger molecule and it is slowly tumbling in your solution. It may be because of the viscosity changes in your solution, whatever the reasons are, it is slowly tumbling. In that situation, you can see differences in your spectrum. So you have the two diagonal peaks going in one direction, and the two cross peaks they have the same sense as the diagonal peak if the molecule is tumbling slowly. But if a molecule is tumbling faster, then you will have the diagonal peaks having one sense, the cross peaks having opposite sign, they are going down below the plane. So in one case the diagonals are like this, the cross peaks are like this. In the other case you have the diagonals like this and the cross peaks are like that, so going down. So this will allow you to figure out whether your molecule is tumbling very rapidly or not in your solution. An illustration of this with regard to application in chemistry or applications in protein structure determination. Once again I say the same dipeptide here, the same dipeptide, and on the left side I have the schematic of this molecule, on the right side I have the schematic of the spectrum. So what all peaks do you see? And I see here all the peaks which are present in the COSY spectrum as well, right. So if you see the cyan peak, you follow the cyan peak H and I. H and I shows me a correlation to the H alpha of its own, which the diagonal peaks are indicated on the diagonal there, H and I, H alpha, H beta, H gammas, they are all on the diagonal. So they are a particular amino acid residue I. Okay, I see a cross peak there from Ni to H alpha, and then H alpha to the H beta. Then I also see from H alpha to the H gammas as well, and H beta to the 2 H gammas as well. Why do I see this? Because the distance between the protons is quite small. If it is less than 5 angstroms, then I will see this peak, because this is not through J coupling, this is through dipolar interaction. If the distance is less than 5 angstroms, I do see a cross peak. Therefore I see from H alpha to not only to H beta, but I also see to the H gammas. Similarly I see from the beta to the 2 gammas. But now you see something else. You see from the amide proton H and I to the betas and also to the 2 gammas. All the cyan peaks are indicating that. The cyan peaks are saying that okay, you see a cross peak correlation from the amide proton to the H alpha to the H beta and to the 2 H gammas. Not only that, you also see another one which is indicated by the green symbol there. What is that? That is actually a peak which is belonging to different residue. And you look at the left, what are those? You see the NH proton has short distance to the H alpha of the previous residue, to the H beta of the previous residue, and also to the H gamma of the previous residue. These are all less than 5 angstroms. Therefore from the NH proton of residue I see to the H beta and H gammas of the previous residue. So first of all you see to its own residue, to its own H alpha, H beta and things like that, but I will see from HNI plus 1. Now we look at the HNI plus 1. HNI plus 1, this is the blue peak on the diagonal. The blue peak on the diagonal is showing you to a blue peak which is to the H alpha of the ith residue, and it is also showing you to the H beta and the H gammas of the two ith residues. All those red arrows which are indicated there, and those are indicated in the spectrum from the blue peak of the amide to the blue peaks which are indicated on the top over there to the various protons of the ith residue. Likewise, you also see from there to some other H alphas, its own H alphas also you will see. These are empty circles which are indicated there. Those are the H alpha of its own residue and the H betas of its own residue, and so on and so forth. Therefore, you see this nosy spectrum has a lot more information compared to what we had in the cozy spectrum. Therefore, typically this is called as the fingerprint of a particular molecule. So let me now conclude and summarize what we have talked about so far. I told you about the pioneering developments that happened over the last several decades, how the field has moved from the basic discoveries in physics to chemistry to physiology and medicine and whatnot. There may be more to come. And I also started with the principle of NMR, the technique per se, how it originated, and what are the fundamental principles which result in the various kinds of applications. And I showed you the fundamental developments with regard to the chemical shift, the coupling constants, and then also introduced you how to measure these various spectra, earlier ways how they were used, and what was the revolution created by the Fourier transform NMR spectroscopy, how it resulted in time saving by order of magnitude, and that made applications which were hitherto not possible. Especially spectra could be recorded at natural abundance of carbon 13 and nitrogen 15, and then this laid the foundation for the development of two-dimensional NMR spectroscopy, and that was another major revolution which happened in the 1970s. And because of that, one could improve the resolution in your spectrum, display the information present in your spectrum into two dimensions, and then of course all those correlations which are present in between the various protons in your molecule can be separated. You can put them along the two different axes. You have more possibilities of display of information. Therefore, you can separate the interactions of, between the protons in an appropriate manner. This resulted in J-resolved spectroscopy, wherein you can actually have coupling information along one side, the chemical shift information along the other side. So this was a kind of a broadband homonuclear decoupled NMR spectra. Then you had the correlation spectra. There are two kinds of correlation spectra, the so-called cozy and the nosy experiments, and the cozy experiments actually displayed it to the J correlations. The protons which are coupled through J coupling, they will be displayed in your cross peaks in your 2D cozy spectrum. And in the nosy spectrum, you had display of information between protons which are coupled through dipole-dipole interactions. And this dipole-dipole interaction actually depends on the inverse 6th power of the distance. The NOE, the nuclear over Hauser effect, is inversely proportional to the 6th power of the distance between the protons. Therefore, it is a short range interaction, and you will see a cross peak between two protons if they are less than 5 angstroms apart. And of course, the intensity will be proportional to the distance there, and if you have a shorter distance, the peak will be higher in intensity, and so on. So normally you don't see a cross peak if it is more than 5 angstroms, and this has great implications with regard to the applications in protein structure determination. I showed you examples of a dipeptide. You take a dipeptide, what sort of a peaks you get in a cozy spectrum, and what sort of a peaks you will get in the nosy spectrum. The cozy spectrum gives you a spin system kind of identification in a given peptide. So if I have a valine residue, you get peaks specific to the valine residue. Likewise, if I had a threonine thing, you would have obtained a spectrum which is specific to the threonine. And for the same dipeptide, I also showed you in the nosy spectrum how you get those peaks which are present in the cozy, but you also get peaks which connect one residue to the next residue, especially the previous residue. Residue I plus 1 is connected to the residue I through various kinds of cross peaks. You have cross peaks from the amide protons to the alpha protons, to the beta protons and the gamma protons, and likewise this allows you to determine the structure of a molecule, because you get so many distance information that lays the foundation for determining protein structures and analysis of protein structures in solution. This was a major development, and that actually led to, as I said, the Nobel Prize in Chemistry to Professor Kurt Wittrich. And Richard Ernst, who was the pioneer of developing Fourier transform NMR and applications in two-dimensional NMR, he won the Nobel Prize in 1991.